So good afternoon. Good afternoon, everyone, and thank you for joining this second talk as a part of our Vision and Language seminar series. And today we have Dr. Fuxin Li from Oregon State University as our speaker. And his main research interests are in deep learning, but more specifically, video object segmentation, multi-target tracking, point clouds, and robustness in deep learning. And before joining Oregon State University, he has held the research position in University of Bonn and Georgia Tech. And he has diverse portfolio of over 50 publications in top tier computer vision, NLP, and machine learning conferences. And today, the topic of his talk is going to be the inner workings of convolutional neural networks and understanding the or estimation of uncertainty in neural networks. And in addition to that, he has won the prestigious awards during his career, like NSF Career Award, and he has won several deep learning related challenges like Pascal Walk segmentation and the Davis Video Segmentation Challenge. That's it. So please join me in virtually welcoming Dr. Lee, and the floor is open for you.
All right. Okay. Thank you, Shailaja, for the kind introduction. Today, and thanks Pietro for inviting me to give this talk. Today, my talk is about mainly some understandings and new designs on convolutional architectures. So this all kind of started with our research in explainable deep learning. So explainable AI has kind of gained quite a bit of interest in recent years. We started working on this starting in I think it's about 2016. And so at that time, it was, of course, known that CNNs had made great strides. There's a lot of benchmarks being beaten. However, there is so people don't really have much idea on how CNNs make classifications. And then without that, it is pretty difficult to trust that deep network to make crucial decisions for you. And this is even true for today. And I think a couple of days ago, I was just reading online, and then there was this news that, there's some face recognition software in China right now. And then you can, or there's also the iPhone, right? You can use your face to unlock your phone. And then some people managed to put some kind of adversarial eyeglasses that you just put on your as eyeglasses, and then you can forge the identity of any person, just like the system will just recognize you as that face. So because it's so brittle, it's very difficult for humans to trust those deep networks unless we can try to understand more of it. So there are a lot of implications in this research. We do have, like, for example, one of the implications is like we want to estimate the uncertainty of those deep network classifiers, which we'll talk later. But first of all, we just want to see how can we understand how does the network make decisions in the first place. So we really want to understand this because more and more there are crucial decisions that are being made by deep networks, airplanes and autonomous driving, things like that. Like for example, there was this, nowadays there were numerous Tesla accidents that were partially kind of stemmed from this. And basically what we want to do is to generate a mental model of deep learning so that humans can understand how CNNs make classification. So at the very beginning, we thought about this idea that, okay, we just look at how do people make explanations. Like the simplest, most straightforward explanations people make are in dictionaries, which usually is of this form, like A is something because of BCD. And for example, this is a bird because it has feathers, wings, and beak. And so usually we can see that B and C and D, those are concise concepts. Those are also high-level concepts. They are they have their own semantics. So prior work, so there have been quite a few prior work that try to use human annotated text and then to try to learn those concepts from those texts. However, the problem with that is that if you use human text, you are already inserting this human prior into the deep network. We don't yet know whether the deep networks are classifying the same way as humans. So it's probably not the right time to insert that human prior this early. So our idea instead at that time, so this work actually started in 2016. So our idea is to instead just try to kind of directly go from the deep CM and then try to come up with reasons A, B, and C without consulting human in the first place. And then once we figured out that, oh, there are reasons A, B, and C, which we don't really know what they are, we can then visualize those reasons. And for example, this reason A, we visualize the features for this reason A, and then you can kind of look at it and you feel like, oh, this probably is the feet of the bird. And then the human can understand the deep network this way. So this was our initial idea. Based on this idea, we then built this network called XNN. We call it XNN Explanation Neural Network. The main idea is like, okay, you take the features from an intermediate layer of the neural network, and then you run some dimensionality reduction, reduce it to human understandable levels like 5 dimensions, and then you use that. So kind of how do you train this dimensionality reduction? You try to mimic the original network. So basically, the network predicts something like this, and then you try to make your low-dimensional features to also make the same prediction. So not only in terms of the same class, but also in terms of the same value, in terms like as a real valued confidence prediction. So we kind of created some loss function, which we said, okay, this explanation features need to be not only faithful, also it needs to be relevant. Cannot include irrelevant concepts. And most importantly, we want to make sure that each X feature here would represent a different concept. Yeah, so we created some optimization to solve this via training. So this dimensionality reduction itself is a nonlinear deep network of several layers of fully connected network, and then there's a linear combination. So we kind of created this loss function. I will skip the formula itself, but so just to show you some of the results later on. But first of all, let's kind of talk about a little bit of the benefits of this. Our results have shown that usually with this approach, you can be almost perfectly faithful to the deep network predictions, which is, I mean, in contrast to some other approaches, which uses human vocabulary. And usually those human vocabulary methods can only be 40 to 50% faithful. So basically, we are kind of on the other end of the spectrum. So if you use the human vocabulary, you are not so faithful, but human can understand it. But if you use XNN, you are indeed faithful, but it's not necessarily that easy to understand. So that's this approach. Besides, the other thing is that if you use something like XNN, if you manage to make the humans to learn the features, maybe they can explain deep learning predictions on a new image. So not only on the current image, but also on a new image. Because, for example, if you realize that the classification is mainly based on feet, then you can say, okay, in a new image, it's still going to be based on feet. So maybe this could create something called we strive for in the explainable AI community is like superhuman capabilities. Like you can have human learn potentially new concepts from this XNN framework. Okay, so we managed to do that, and well, we made a user study, so we managed to train a network based on the previous principles. So we try to see whether XNN really helps humans to learn. So we made a user study, and so in this user study, we tried to find like really difficult classification problems for humans. because if you just use normal natural images, classify cats and dogs, humans don't really need to learn from the network. They already know how to classify them. So we kind of went with just really difficult tasks. So we found two tasks which we thought might be difficult for humans. And then the first one is coming from biochemistry, actually biophysics, where we gave the humans some different categories of cell fluorescent microscopy images. We managed to exclude all the participants who are experts, so they really don't know how to make this classification, and all their learning is in our user study. They have a learning phase. And the other thing we did is like this fine-grained seagull classification. So those are all seagulls, but they are actually 5 different types of seagulls. And then we asked the humans to learn from the network how to classify them into 5 different types of seagulls. And this is extremely hard because even I mean, not usually people don't have any idea. They all just look like seagulls. So we have basically some kind of mixed results on this user study. So on the cell microscopy data set, we thought it was hard, but we ended up realizing it's not really hard enough. So humans basically did about the same with no visualization and with XNN. So however, a previous visualization, a previous heat map approach actually made human performance even worse. And then on the seagulls data set, we managed to kind of notch some improvements. With the XNN predictions and then with the XNN visualizations, humans were actually able to improve their performance on the seagull classification data set. And so we realized that our goal to actually improve humans is not that straightforward. Of course, you really need a very hard task. So that's the main takeaway from this first endeavor. By the way, please feel free to stop me with any questions at any time. Feel free to just unmute yourself and ask it. Yes, go ahead.
There was a question, not from me, but about what faithful meant in the previous slide.
Well, faithful just means that your explanation network would predict the same, like your explanation will predict the same output as the network that you are trying to explain. That's faithful.
Hey, Professor, this is Weidong. I have a question here. My question is, XNN helped humans to identify seagulls with a higher accuracy. Is that because the human will look at the picture, but also use your heat maps as a reference point?
Right. They use they not only look at the picture, but they also look at the heat maps generated from XNN, which I should have shown more individual examples, but this is like one of the example of one of the features. But in practice, they see like multiple 5 different features generated from XNN.
So that has to be based on the fact that the pre-trained results is much higher than the human results, right?
Yes, the pre-trained network has pretty good accuracy on this data set. And then like untrained human don't, because I mean, if you are a bird expert, then you do, but if you're not, then no.
Got it. Thank you.
Yeah.
Professor Lee, I also have one question. How does this XNN trained? So in the previous slide, you showed that it know that it is a bird because of ABC. Do you give the reason ABC to train XNN?
No, you don't. So you just train this to minimize the kind of, there is a 3-part loss function. It tries to minimize it tries to be very faithful. It tries to make each features in this low dimensional space to be orthogonal to each other. And then it also tries to not include irrelevant concepts. So we put a 3-part loss function and then train it on. So first of all, we already have a trained neural network, and then we train this XNN on this already trained neural network. So we fix the network and then we just train this part.
So there is one more question. Is XNN trained together with the base CNN?
No, the base CNN is trained first, and the XNN is trying to explain the base CNN.
So do you see some sort of disentanglement in that feature space? Like, do you see that some parts of the features correspond to a beak?
Yes,
stuff like
yes, that is happening. So let's see, if you want to see more visuals, we can kind of go to the paper, and so there are kind of more visual results over there. So should I put it in here? But yeah, so later I can show you some more visuals, but the real reason I kind of started with this is because this is our first approach, and by doing this, we realized that I mean, we don't always succeed. Actually, more times than not, we don't succeed. And one of the problems we kind of realized is, give me one sec, maybe I can show you a few more visuals before I move on. So let's see. Okay, here. So here. Here. Okay, so I can show you some visualizations of XNN. So you can see that, for example, if this is like this thing is called a license albatross, and then the first X feature ended up to be the eyes, and then the second X feature looks like it falls on the wings of many of these birds. So those are, yeah, some examples. Yeah, but what we did realize is that it doesn't always work. And one of the reasons we thought might be why it doesn't always work is because our heat maps weren't really great. So we utilized kind of existing heat map methods to visualize those networks, but we realized some of these heat map methods are kind of bad. So for example, in the middle, you have this heat map method, which is called mask. And then it kind of looked reasonable. But then if you just remove this heat map part from the image, you can see that the CNN still classifies the same bird with more than 90% probability. And then if you only show this heat map part in the image, and then you blur everything else, you can see that the CNN still cannot classify this bird. So a lot of these heat maps, although they look reasonable, they are not really representing what the CNN is actually looking at. So this has also been found later by kind of a lot of other people. So there were a lot of nice papers that showed that, oh, these heat map methods don't work. And unfortunately, maybe there has been too much of a distrust on heat maps nowadays, rather than too much of trust in the early days. So what we did is we ended up kind of going to say, okay, now let's not try to shoot so high. Now let's just try to shoot lower. Let's just try to make the heat map to work. So what we think would be a working heat map is that, first of all, it should kind of indicate the important features in the image. And for example, if I remove this highlighted part of the heat map, for example, so if you look at this one, we have this mask, which is part of our heat map. And then if you remove this part, the CNN should no longer predict this class. And then if you only show this little parts, this is the part of that the heat map reveals, then the CNN makes the same, makes a confident classification. And this really shows that the CNN is indeed looking at this heat map when it is making these predictions. So what we did is that instead of kind of using previous methods, we developed a new method called I-GOS, where we use optimization instead to optimize for a mask that will kind of achieve what we want it to achieve. So in the first version of I-GOS, we are just we are just optimizing for the smallest mask that will reduce the CN prediction score. So in other words, we are basically just optimizing for the center image. So we are trying to find kind of, you think about this optimization problem, you are already given the neural network, and then you're given this image. You're optimizing for this mask, a pixel-wise mask. And then if you apply this mask to this image by blurring it off, and then the CN will no longer predict this class. You can kind of think about this optimization problem. And that's what we did. But we realized that if you directly do optimization, this doesn't really work, because this one is a very highly non-convex optimization problem, and it's really easy to get stuck in a local optimum. So what we did is kind of a weird approach, which is like, instead of just using normal gradient descent, we realized that this is a very special optimization problem, in the sense that, okay, the goal of our optimization is just for the CN to predict 0. And we know when does the CN predict 0. CN, if you just give the CN a blank image, CN will predict 0. So we basically kind of know the global optimum of part of this objective function in this problem. But it's only part of the objective function, because we also are looking for the smallest mask. We don't really want to mask all the pixels. So conceptually, this can be shown as this constrained optimization problem, where we actually know the unconstrained global minimum here. And then we know there is this constraint that we need to satisfy. So we cannot directly go there, right? You just show a blank image, that's not really what we want. So instead of just directly taking gradient descent, which might lead you towards this point C, because it is a local optimum, what we did is we take this integrated gradients, which is like computing gradients not only at this point, but also on all the points in the middle. So, and then we sum all the gradients together. And this kind of leads us to not to go to this direction, but go to a direction that is significantly better and kind of leading towards local optimum. The global optimum. So something like this. So instead of going to a local optimum, we realized that this performs significantly better than the original approach of just running gradient descent. And besides, we introduced, well, this was not our introduction, but we kind of followed this new metric of evaluating heat maps, which really tries to just delete the heat map and insert a heat map just to see whether the CN still makes the same classification. So if you look at this, you can delete a little bit of the heat map. And then what you can see is that in this case, the CN is no longer making any confidence classification. The classification confidence is dropping towards 0. And then if you only review just this little bit of the heat map, the classification confidence is going toward 100%. So this really shows that we are finding a heat map that is correlated with the CN prediction. In this other case, you can see this as well. So you can see at this point, if I remove this heat map, then the classification confidence drops to about 10%. But then if I only reveal this part of the heat map, it's already 100%. So this gives you a little more insight on what the CN is looking at. So if you kind of compare this with some older heat maps, for example, this very famous algorithm called GradCam, you can see that the heat map we generate is just very, very different. And then the GradCams sometimes don't really score very well on those deletion and insertion metrics. They actually score very poorly on, especially on the deletion metric, because GradCam just tends to generate a lot of heated points on irrelevant locations. But our heat maps are kind of small and concise, and then it is really correlated with the CN prediction. And especially if you look at the heat map, yes, was there a question? Oh, sorry. Yeah, especially if you look at the heat map we generate versus this excitation BP, which was actually what we used when we started doing XNN. You can see this excitation BP just makes completely erroneous heat maps that has nothing to do with the classification. So if you delete this heat map, the classification score never changes until you almost delete the entire image. So that really means it's just a wrong heat map many of the times. Sometimes it looks like it makes sense, so it's very hard to realize that those heat maps are wrong. And so we recently further improved the I-GOS to I-GOS++ by, realizing that the smoothness, well, I-GOS didn't really do a good enough job in like long and thin features. And then sometimes I-GOS would just break a feature instead of identifying the feature. So because when I showed this, we realized I-GOS only optimized this middle image, but we should also optimize the image on the right-hand side as well. So we should kind of jointly optimize that the CN should predict very low if I remove the heat map, and then the CN should predict high if I just show the heat map. That's straightforward. But so putting this together and then also kind of getting some more improvements in terms of, sorry, not this. In terms of using a bilateral total variation term for smoothness, we were able to get significantly better performance in this new version called I-GOS++, especially on objects with long and thin parts. So if you kind of measure the metrics in terms of this insertion and deletion metric, I-GOS++ really significantly improved over everything else, including I-GOS and GradCam and so on as well. So, and then it also works very well in high resolutions. So the problem with GradCam is it only works in very low resolutions, but I-GOS++ can work almost at any resolution. And so some more visualizations here is shown for I-GOS, I-GOS++, and also other heat map methods. And you can see that the metrics, the insertion and deletion metrics for I-GOS++ is just significantly better. And especially it is still good under a very high resolution. So if you look at this very high resolution, then it is kind of just looking at this very minute details of the object, and here as well. So it really finds the correct details in the object. Whereas like if you look at GradCam, it just pointed right in the middle. It doesn't really do anything. And then, so yeah, so these are just some more visualizations. I realized. So there were some more questions. How are the heat map and the optimization method? So the heat map is basically the mask that is generated by the optimization method. So we just output the mask generated, which is optimized. So given a fixed network, and then given our optimization objectives to reduce the CN scores the most, given the mask, and then to improve the CN score given 1 minus the mask. And then you just output the mask.
Fuxin, I have a question regarding the evaluation matrix you are using by deletion and addition. Is it also an overall evaluation matrix goes over multiple image testing cases, not only a specific image by image evaluation in this field?
In this particular figure that you are seeing right now, this is on that particular image. And okay. Then in the previous table, it is average over the entire ImageNet data set.
I see. I see.
Thanks.
And I do have another question. Compare with blurring the rest of the image. A straightforward way to do it is typically just wipe it out, right? Instead of blurring the rest of the image. Do you guys observe whether the blurring actually, or the level of blurring, have any influence in CNN?
Right, so that is a great question. So why do we not wipe it out? because we realized even from early times when we were doing XNN that if you just wipe it out, it actually creates a mask. Like if you wipe a certain area out, then it creates very strong boundaries around that area, because then that part is just black and then the rest is not black. And CNNs, we realized that it really looks for boundary features, because if you think about convolution, that's captured in the first layer. So that actually misleads the CNN, and then it looks for the features on this map, on this kind of blacked out region of like the boundary of this blacked out region. So creates a lot of error erroneous classifications. So that's why we, in the end, decided to do this blurring operation, which does not create boundaries.
That makes sense. Thank you.
So a related question in the Dalmatian, like the dog example, you showed that 1 minus the mask. Like if you show the spotted features, the CNN is able to predict better. So do your heat maps also reveal like ways to create adversarial examples then? Because if you know specific features that your classifier predicts as this class, you could add them onto an image.
We haven't really tried adding them to other images, but yeah, that's a very good idea. I think you can try it if you're interested.
There is one more question. Does the I-GOS++ work on any convolution net?
Yes. In principle, we have tried it on UGG and ResNet, but you can feel free to try it on other networks as well.
Is a heat map a pre-processed version of the image as input to the CNN, or it is a output of the CNN? I'm confused about the concept.
This is an output of optimizing based on the CNN. And then, so when we were evaluating this, we are giving these images to the CNN. So this is like the image that is masked by the heat map. We are giving those images to the CNN for evaluation. The heat map itself is an optimization based on the CNN, based on a trained CNN.
Okay, thanks.
Okay, so with that, we actually kind of recently made an interesting application of this heat map approach. So what we initially thought is, okay, we know everybody is kind of looking at COVID right now. And then we initially thought maybe those heat maps can give us some interesting insights onto how, I mean, like how do you actually classify COVID-19 with X-ray imaging? So we basically run I-GOS++ on this classifier that is trained on a COVID-19 classification data set. And so initially, so first you have a classifier and then you run a heat map on it. And then we realized that the heat map doesn't really do what we wanted to do. Actually, in many cases, not all the cases, but in quite a few cases, the heat map just focused on one character at the side of the image. So if you look at this I-GOS+ heat map just focus on this R. So we did a little bit of further kind of investigation of this. And then we realized that if you just put the R there and then you put the arrow there, you can already classify this as COVID. So this X-ray, the classifier thinks is COVID without even seeing any part of the lung itself. It's COVID. And on the other hand, if you just show the whole kind of COVID X-ray, just getting rid of this R, it's no longer COVID. So reveals that it happens to reveal that this heat map method reveals some of this overfitting issues of the deep network. So it's like the deep net, this almost looks like an adversarial example. So you could put, happens to be that in more COVID X-rays, there are this R, and then the classifier picked that up and then just decide to classify on the R over there.
Why is R being identified being the focus of the heat map?
Because the classifier used that to classify COVID.
So for the negative data, there's no R over there.
Maybe just less R's in the negative data. Just happens to be this data set. I mean, it should be exactly random, but you just cannot control everything. So it may happen to be there are more R's in the COVID images. And then the classifiers, during the training of the CNNs actually picked this feature up, thought this is the COVID feature, just the R and the arrow. So yeah, those are COVID features, without really looking at the X-ray image itself.
So what is the semantic meaning of R in the medical term?
It's just right. It just stands for the right-hand side.
Oh, I see.
Of the chest. Yeah. So you sometimes they put an L, sometimes they put an R just for left and right. It's nothing special.
Is that a issue caused by the heat map or caused by CNN?
Caused by CNN is because the CNN is trained to pick up this R as a feature to classify COVID.
Okay.
Yeah, so we actually, in the end, so we use the text detection. So after we figured this out, we use text detection and in painting to get rid of those characters in the X-ray image. And then we created this new data set we called COVID++. And then we realized that if you train on this new data set, it actually generalizes better to the testing set by about 2%. Not really that much, but we seem to have found a small bug in the convolutional networks classification. So we are still really trying to look at whether we can get real useful features on COVID, but this is what it is right now. So the rest of this is still ongoing. So with that heat map, we also realized another thing. After we worked a bit on heat maps, we realized that maybe heat maps are really not the right way to do it. Because the insertion and deletion, when I showed you the dog with the dog, it was symmetric, but sometimes it's not symmetric. Sometimes you have this heat map and then you delete this heat map. However, the CNN is still classifying it at 100% confidence. And then you insert the heat map, this is correct. Indeed, if you insert this part, CNN classifies it as 100% confidence. But if you delete it, the confidence never does drop. So we realize that CNNs are not that simple. You cannot just use one heat map to explain the CNN. So for example, in this school bus, in the case of this school bus, you can totally find 3 totally different heat maps. And then if you highlight those 3 totally different heat maps, you can all get the bus with like 96, 99% confidence. So really, CNNs are not that simple. You should be looking at not only one heat map, but multiple, maybe a logical structure like this or that, to try to explain the CNN classification. So this is our most recent work where we showed, instead of one heat map, we showed this whole bunch of things, whole bunch of maps that try to explain the CNN with a more logical structure. So not only one heat map, you can see here the root nodes are 3 different heat maps. And then we also show that if you remove a piece of it, how does the classification confidence evolve? For example, in this one, this is 99%. And then if you just remove this part, this becomes 8%. And then if you remove this other part, it's still 85%. So it's not really that bad. So with that, we try to kind of create some more like logical structures in terms of explaining CNNs. And so we try to see whether this would help the users better than just showing them one heat maps. And then the kind of study here we run is to ask the users to make kind of a new, make a classification on a patch, on some patches that they have not been shown. So like we already showed them a lot of heat maps, but then we ask them, so we give them 2 new options. Like this new option is heat map is here, and then this new option heat map is here. And then we ask them which option is more likely to be classified more confidently by a CNN. by the CNN. So we make sure that this option was never shown in the kind of structural attention graph that we actually showed them. So we call this method SAG, structural attention graph. We asked them to predict whether this is more likely to be classified as more confident from the CNN or this one. And then we compared with baseline single heat map approaches, such as I-GOS and GradCam. So we realized that it is like if you just show them the regular one heat map approach, it actually does not really help them in terms of identifying which of these two is more likely to be confidently classified by the CNN. So if you look at this, like I-GOS, GradCam, they all actually reduce the score of the users in terms of predicting CNN behavior. And so SAG, without kind of those arrows, so here I didn't show, but there are some arrows here in the SAG that we highlighted just to show the users what are the relevant things. Without those arrows, users just look at SAG just because it's just too much information. The users cannot handle it. So without the arrows, the users also don't do very well. But if we kind of show that, okay, this is the part of the heat map that is kind of related or that is close to this patch, if we kind of show those relevance arrows, we call it interactive SAG. And then you can see the user score jumped by kind of 3 questions when it is shown in the interactive SAG. So you can see all the others. There is basically no difference between showing no visualization and showing some visualization. Only with interactive SAG, the user performance jumped by 3. So here you can see that, first of all, you want to show users not only one heat map, but multiple of them. And also you need to guide the users through so many visualizations. Just showing so many things on its own is not quite enough. Yeah. So I guess I did spend a lot of time here on all this. Let me see. Yes, I will. So I will send you the slides afterwards, and then we have the links to all these heat map papers. And it's not I-GOS++. This is answering the other question. I-GOS++ is not trial and error. It is an optimization problem. It is an optimization problem that is solved by running integrated gradient descent. Okay, so I already spent a lot of time on explanation. So let me kind of quickly go through the next thing, which is what you realize after doing so many visualizations of CNNs. So we realized that deep learning is totally reliant on memorization. And many of the times they are just say, okay, if there are many different eyes, they are not really having one X feature that is covering an eye. However, they can find an X feature that covers a small eye, and then they find another X feature that covers a big eye. So like they have no scale invariance, especially. They have no scale invariance. For any different scale, it needs to remember a totally different feature. So that is one of the big takeaways we found from doing all this explanation research. And then here I show you some examples of things kind of being mistaken when you show CNNs images that are in unfamiliar scales. For example, in this case, this is like a toothbrush, but it's unusually large, and somehow it was misdetected as a person. And then this one is kind of somehow becomes a chair. Maybe because it looks like it, but it's just in a very unusual scale. And then here, it also misses small objects like the phone here. So here, supposedly you want to detect the phone as well, but it was missed. And kind of moreover, we showed some results that really show that CNNs are not good at scaling. So here we showed kind of accuracies of training the CNNs on very small resolution, and then testing on larger resolutions. So if you see here, we train on 14 by 14, 16, and 18. And then if you test on 28 by 28, the accuracy is still reasonable. This is just MNIST, so it should be fine. But if you test on 56 by 56, like if you enlarge everything 4 times, then there is almost zero, it's almost chance already. So, I mean, it's very simple to explain this because the 3 by 3 neighborhoods in CNNs, if you kind of enlarge the image, the 3 by 3 neighborhood is kind of falling on a totally different location in the image. Yeah, so that's part of the things we actually learned from doing XNN research. Now, what we can do, we actually will skip those prior work. There are spatial transformers, deformable CNNs, but it works with small transformations, not large ones. Our goal is to compute convolution, not on those 3 by 3 grids, but on arbitrary point sets. So this would also generalize to beyond cameras, such as LiDAR, sonar, and tactile sensors. So here, the idea here, there are some prior work which I also skipped. So the main idea here is that instead of kind of, this is the raster CN, you kind of, maybe you can take a look at this formula here. So for each location, we have a W. And then, so for example, this is 1, 1, minus 1. So those 3 kind of delta locations are the inputs of, or the subscript of the W, right? For each location, we have different W. And then we also multiply that W with X of I plus delta I, J plus delta J, K plus delta K. So basically, we multiply W with X with the correct offsets. So this is the conventional CN. What we want to do instead is a continuous domain CN, where W is not having those subscripts, but being a function, like a continuous function that has the input of these 3 delta subscripts. Like 1, 1, minus 1 would be the input of a function, and this will be a convolution function. So the main idea here is that this convolution function can actually be approximated with a neural network. So this neural network takes in 1, 1, minus 1, and then it outputs the weights of the convolutional network. And then it also takes in 1, 1, 1, and then it outputs a different weight. So this is the idea, approximate this convolutional function with a neural network. So it's an important idea. Now we can just send in any delta I, delta J, delta K, and then we can get a different weight function. So then we can just run convolution on any points, arbitrarily spaced. We can also do, another thing we can do is we can make it scale invariant just by normalizing those delta I, delta J, delta Ks with respect to the global scale. And of course, we can also do something better than that, which I probably won't have time to show, but I can kind of briefly talk about it. So it turns out that this is not exactly new. There was some prior work that did this approximation, but we went one step further in that we found a very kind of efficient way to compute those. Because normally, if you try to estimate the function for all the convolutional weights, that's a lot of weights to estimate. A convolutional network is huge, right? There's a lot of functions you need to estimate. We found out that there exists some kind of change of summation sign idea where you can just use, and then you don't really have to explicitly generate all these convolutional weights, but you can still compute this kind of implicit convolution. And that's our point conv. It is more than 60 times more memory efficient than to directly generate all the weights by fitting an MLP to fit each weight function. So we can also do, I mean, downsampling, upsampling, deconvolution, everything you can think about convolutions, you can do it with point conv. If you turn a 2D image into a point cloud by just treating every pixel as a point, you can still do that, right? And then now you just switch your neighborhood, 3 by 3 neighborhood. Now we use k nearest neighbor neighborhood, and then 9 nearest neighbor is exactly 3 by 3. So it's the same thing in 2D. And then we can match the accuracy of AlexNet if we use 5 layers, or VGG if we use 19 layers. So it is a real convolution. And then it performs, it also kind of works if you make proper design choices, like an epsilon ball neighborhood and certain weight function choices, it can actually scale. it can kind of be scale invariant rather than the original CNNs being not scale invariant. It also works very well on 3D point clouds, like semantic segmentation data sets with point cloud as inputs. Besides, we can also kind of create, because those delta I, delta J, delta K, there are ways to just change the input first before sending them as an input to the weight function. So you can actually also make them rotation invariant as well. So you can kind of just create a different coordinate frame. That coordinate frame itself is rotation invariant. So you just change the coordinates, and then you have a rotation invariant architecture. So we did that, and then what we found out in the end is that the best approach is to give them the XYZ, and then give them the rotation invariance, and then give them the scale invariance. Just put everything together in the input, concatenate them, and then use those as the input to the weight function. And we realized that will give us like state-of-the-art results for any point-based network on a large benchmark called semantic Kitty, which is semantic segmentation on the Kitty dataset. It can also be applied into many other different domains, such as like you can think about a lot of things as point clouds. Just, I mean, anything that's irregularly spaced in low-dimensional Euclidean space. Letter stations, RTS game units, and then also temporal stuff. We also had a really interesting application for point matching. So people used to use ICP for 3D point matching. That's really bad. And then the good way is to run cost volume. So if you work on optical flow, you will know that people work on cost volumes, and then they do matching by first computing a cost volume between one pixel and a lot of neighboring pixels on the other side, and then generate a huge cost volume and then performing convolution on this huge cost volume. So now we have point count. So we don't really need to generate this huge cost volume. We can just discretize this very large cost volume onto k nearest neighbors. So in the end, we can create a point-based cost volume, which is just based on, first of all, skip this animation, basically k nearest neighbors on the first frame and k nearest neighbors on the second frame. So oops, there's too big of an animation here. But basically, the point is that you can use point count to directly compute convolutions on the cost volume without really needing to instantiate a 4D tensor. And this is the current state of the art in non-rigid 3D SymFlow, which is like non-rigidly matching a lot of points in the 3D space. So if you look at this video, you can see that the purple point cloud is the first frame, and then the green point cloud is the second frame. And then they are matched by using Point-PwCNet, which is what we proposed in ECCV 20. And you can see that different areas are undergoing a different transformation because this is just totally non-rigid. Each point is actually computed its own matching. But you can see that it matches really well. It also runs at 10 frames a second. So it is a lot faster than the previous non-rigid point matching approaches. OK, I think I'm almost out of time, so I will skip this last part of uncertainty estimation. I can give a one-slide overview that what we did is, we will kind of get rid of all this, but what we did is we generate a neural network instead of training a neural network. And by generating a distribution of neural networks, we can actually sample different neural networks, and based on the disagreement of this sample, we can compute a really good uncertainty estimate of the neural network. So each of the networks may be overfitting to its own side, like, yeah, it's just overfitting this way, and then the other one is overfitting that way. But if you average over the entire distribution, you actually get a really nice uncertainty estimate. So don't really have time for actually talking about this, but we have a couple of papers in recent ICMLs about this generative deep networks. So yeah, that will be it for today's talk. And I thank a lot of collaborators, including my students and the other professors at Oregon State, as well as people from Horizon Robotics and Neural. All right, so now I welcome more questions. Thank you.
Thank you, Fuxin. Can you hear me? All right. Let's open the floor. There's actually a couple questions already on chat while you are going over the last part of your talk.
I guess that was asking for the PowerPoint, which I will send it to you. And I think I already answered all these other chat questions.
My name is Jianming Liang. I have a couple questions. Actually, it's related to your first part of the talk. It's about the faithfulness. Somebody already asked this. How you define, so have you measure some kind of objective measure to see your interpretation is faithful? How you gonna measure your faithfulness?
Oh yeah, we actually have a couple of different measures, and for that, let me pick it up. Let's see. So basically, we have, when we are evaluating the faithfulness, we evaluate first the classification version, which means whether the XNN will make the same classification as the deep network is trying to explain. And then we also measure the kind of real valued version, where we use the, I think it's a mean squared error between the, so it's just a regression cost. There are some tables I didn't really get to show in the talk, but yeah, so we have a measurement on the classification, which we showed that XNN, this is our XNN approach. It's like 99.99% faithful, generating exactly the same classifications as the CNN it is trying to explain. And then also in terms of mean squared error, it is just having a 0.08 average mean squared error with respect to the CNN it is trying to explain.
You have a slide talk about human language interpretation. You said 40%, 50% or something. So how you compare your, how to compare this to kind of faithfulness?
Our faithfulness is kind of with the same metric. Our faithfulness is 100%.
I mean, you also measure the language interpretation faithfulness in the same way?
It was not our paper, but they measured it in a very similar way. Yeah. Like how many percentage of the network prediction can that language-based explanation explain? And I don't really have the exact number, but I think the result is in the 40s.
Okay, you also have application about the cell interpretation and the X-ray interpretation.
Right.
So did you check the interpretation with whatever experts, or you are based on ground truth, just ground truth?
We are based only just on the trained CNN network. We don't have any human input in our explanation.
Okay, I see.
Hey, Professor, I have a question here. Sweden again. In your paper, you mentioned that from your E space, you let me see how to say it. You regenerate a sparse input. Input.
Right.
How did you define the weights? Are those weights independent of the input direction?
Right. We actually don't have the weights. We don't have weights. We just do so you actually read the papers. Yeah, I didn't really get to talk about this because I don't think I have time. But yeah, so in the paper there was a reconstruction loss that will reconstruct the intermediate layer. Right. And then and then over there sparsity is obtained by having just a robust loss function on the reconstruction loss. So if you have a robust loss function, then your loss does not really increase too much if you just make a total mistake.
How do you determine the factor? Because it is sparse. How do you say it is sparse enough? 80%, 70%? how do you know which of the nodes are the primary nodes to be identified?
Yeah, that's a great question. So that is based on parameter tuning, I would say. We tuned for our metrics over there, which is faithfulness and then orthogonality. So here, O is orthogonality between different X features. And then we also have another metric which is related to disentanglement in the sense of like how many parts is each X feature capturing. So yeah, but the definition of this locality metric is quite complicated, but it roughly refers to the number of parts that each X feature is capturing. Actually, it is the log of that. It is actually the entropy. So if you exponentiate that locality number, that's pretty much the number of parts that each X feature is capturing. And it is only defined on those fine-grained data sets where they actually have part annotations. So, and then we basically have this algorithm. It has a bunch of parameters. We can just tune them based on those metrics. Because you cannot do a user study for each parameter combination of your XAI algorithm, and that's going to be crazy.
Mm-hmm. So is your three-part loss function a brand new idea?
I think it was when we first did it. So this was first published in a New York 17 workshop, and then at that time, I don't think anybody did that.
Great.
I have a question. So you found through these papers that there's local maxima that different networks will converge to, and particularly in the attention domain where they'll have these small subsegments that different neural networks can learn from to achieve maximum accuracy. Why do you think the they get cut into separate segments instead of looking at the whole picture? Is that some sort of like sparsity constraint that's put on the network? Or because would it be beneficial to be looking at the whole, to all the different segments, right?
So I don't quite understand the question. You are asking about attention-based networks, or are you asking about heat maps? Because these are totally different things.
Yeah, I was tying it to attention, but I suppose I'm referring to heat maps because that was what was discussed in the presentation. Right. And in the heat maps, you have, you basically say that there's different regions that the network could learn from and potentially get probably just as high of accuracy, right?
Right, for example, here. Mm-hmm.
Yeah, and so and so why does it get fragmented like that? Why does it get split? Why doesn't it look at the whole region, right? Is that because there's some constraint on the network to look at or constraint to look at as small of a region as possible?
Oh, okay. So part of it is because we were optimizing, and then we have certain constraints on continuity, and then those constraints are kind of tailored to make them to not be too strong, and so that it does tend to find the slightly kind of disconnected parts, and I think that's normal. And but kind of a deeper answer to this is that CNNs are very local classifiers. So CNNs just look at very local features. So if you think about the CNN, it starts with this 3x3. So what can 3x3 do? It can find a local gradient, meaning something like an edge. And then those kind of activations just get propagated into ladder layers. And then finally, they got put together in some way. But a CNN is not necessarily looking at all the parts of an object. It is mostly looking at a few very prominent textures, and then some prominent kind of shape like boundaries. And so those are the kind of things CNN use to classify, not everything. So if you look at this, one of the things here is like, if you look at this, and for a human at this point, I mean, that's still a perfect, this one is still perfectly identifiable. However, for the CNN, it is already about 0%. So what that means is that CNNs are really kind of looking at these very salient features, especially the face of the dog. You can see a lot of the times CNNs are just, I mean, when CNN classifies a dog as a certain type, it's looking at the face of the dog. It's not really looking at fur and other things. It is just starting from, if you think about it, starts from 3 by 3. It just looks at very local features.
I see. Yeah, that makes sense.
Mm-hmm.
So one participant is suggesting that can we reorder the regions detected by the heat map randomly and then evaluate these models? So what do you think about that? Will it help to create better architectures in the sense that the models can have better sense of directionality?
We reorder the regions how?
I think what he means is when you are showing piece by piece into insertion, the order is determined by the value of the heat map right now.
Right.
Then this sequence actually matters, influencing the final output of CNNs, because if you reorder the regions, no, I don't know whether you guys did this experiment, but I suppose the performance will be.
You can, yes.
Well.
Thank you. Yeah, thanks for the rephrasing of the question. I think, yes, we actually did that experiment, and in quite some cases, it can improve. You can actually just kind of, you can do a complete search based on a heat map, like or a heuristic search based on the order of the heat map. And then, yes, you can get a better heat map. We did that, but the thing is, right now we are kind of trying to argue that one heat map is really not the way to explain the full spectrum of CNN decision making. So basically, what we can also do is, based on that kind of heuristic search, we can find multiple different heat maps that all would explain CNN. And that's actually what we are doing now in SAG.
So do we have time?
Yeah,
we have time.
We still have. Oh, if Fuxin is not,
I'm fine. Yeah. I'm
other appointment. We still have a couple minutes. Go ahead.
Yeah. So my question was about the point cloud work. So you showed that it works pretty well at different scales, in the sense that if you have a high resolution image, but what if your digit itself was larger, like occupied a larger area of the image? Does it still?
Yeah, that would be okay. That would be okay too. Yeah, because what we did in the end here, we actually did global average pooling at the last layer. So just following, say, ResNet or kind of any recent architecture. Where is the 2D? There's the 2D result. 2D result is here. Yeah, so we just did global average pooling. So it doesn't really matter where the digit is.
And then in the case of you said something about rotational invariance, but does that mean that you can, without training on rotated MNIST digits, you can classify rotated MNIST digits?
So unfortunately, our rotation invariance only works in 3D because in 2D we don't have that extra dimension to create an invariance coordinate frame.
Right.
So in 2D we don't really have very nice rotation invariance, but in 3D we do. So basically, I really jumped through this, but the main idea is that you can create a rotation invariant coordinate frame by first looking at, so if you think about, there is a center in convolution, there's a center, and then there's another point, and then there is a vector between this center and this other point. And then in 3D, each of this has a surface normal. So each point has a surface normal. So these three vectors, you can just do some Gram-Schmidt on them. Then you can generate an orthogonal coordinate frame. And then what you can do is you can just take the angles of the normals with respect to this coordinate frame. And you can show that those angles are actually invariant, because when you rotate this thing, you rotate both of these points. Both of these points, and then this whole coordinate frame, because your normal also rotates, right? Everything rotates simultaneously. So this whole coordinate frame rotates simultaneously, and that's why your angles are all rotation invariant.
Okay, yeah, that makes sense. Okay.
Yeah. So unfortunately, this doesn't work in 2D because we don't have this extra information.
Yeah, that fundamental problem is still a huge deal right now.
Right, but in 3D we can. In 3D we can make this totally rotation invariant.
Okay, thanks.
All right, any other questions?
Yeah, Professor, I have one question. So you said that CNN always look at like a local feature, and you also said that maybe there are multiple feature map can explain the decision. Does these two contrary to each other? Because I think that if CNN only look at the local feature, then maybe there is only one feature map that can explain its decision.
That's actually a pretty good question. But I think, I mean, you are underestimating it. The point is like, okay, locally, yes, it's looking at different local features. But if you think about ladder layers, right, and then so there's a lot of activations, and then all the different activations are somehow activated, right? They are all, if you think about this as like after ReLU, they are just all positive numbers. So there are a lot of positive numbers in the last layer. And then that final layer, if you think about that final layer as a linear classifier, then it can take, so a linear classifier is an OR relationship if you think about it in logic terms. So suppose there's like 3 sets of different evidences, and then this one will give you a 5. This one will give you another 5, and then this one kind of gives you maybe 5 plus 5, maybe it gives you 10, right? So these are 3 different regions, and then you can get 5, 5, 10. After softmax, as long as you are reasonably large, so suppose your kind of activation is reasonably large before softmax. After softmax, it will all become 99%, because that's the way softmax works. As long as this number, so for example, for the school bus class, the number is 5, and then for all the other classes is 0, then it gets back to 99%. On the other hand, if it's also 10, if it's 10 and then all the other classes are 0, it also gets to 99%. So in the end, the final layer is a sum, right? The linear classifier is a sum. And the sum, if you convert it to logical terms, is an OR relationship. That's why CNN in the end can have just multiple different explanations based on different activations, because in the end, it's a big OR of everything.
Okay, I see. Thank you.
Thank you.
Thank you, Fuxin. I think we should cut off here since we are already running over time. Thank you again for joining our seminar. It's really an informative talk, and have a nice day. And hopefully we can see each other in person in some in-person meetings fairly soon, later 2021, hopefully.
Yep, hopefully everything will become normal. And thanks again for the invitation, and thank you.
Stay safe, stay well.
Yeah.
Thank you. Bye-bye.